let's talk about feature extraction. So, what is feature extraction and why is it needed? Models don't understand raw data, they just understand numbers. So, feature extraction is the art of converting our real life information into useful numbers. So, raw data is not directly useful for our models. So, models need clean, meaningful inputs, and the better the features, the better will be the performance for the model. So, what we do is we collect raw data, we extract features, then we pass it through the model, and then we get the prediction. Now, we'll see a simple example. So, let's say we have a tabular data, we have height, weight, BP, and we are predicting heart disease. So, now height and weight directly is not useful to predict heart disease. But if we calculate BMI from height and weight, that can be indicative. So, that can tell something about the chances of heart disease. So, we'll extract BMI from height and weight here. So, this is one simple, very simple example of feature extraction. Now, how features are created? So, if we have a categorical data, so let's say yes or no, male, female, or let's say colors like blue, green, red, right? So, how we'll represent those data? So, we represent it either by sequence or one hot encoding. So, blue can be 100, green can be 010, red can be 001. If we have some symptoms, so let's say I have some raw text, or maybe I'm saying that I have fever and cough is worsening. So I told cough 2 times, right? And fever 1 times. So based on the frequency of the words, we can come up with some embeddings. So this is based on the frequency or counts of the data. So we will normalize few features like BP, age and all. So that is also kind of, we can say, feature extraction or feature improvement. There will also be some domain features like BMI, risk score, etc. So different domains will have different types of features. But in general, there are two most popular feature extraction technique in machine learning. One is PCA or Principal Component Analysis, and another one is SVD or Singular Value Decomposition. So for PCA, I have already created one video. If you have time, you can go through that to understand it better. But what PCA does is, it's used for dimensionality reduction, simplifying complex high-dimensional data into fewer, more manageable principal components. So these principal components are the new features, while retaining most of the important information. So if we have, let's say, 5 or 10 features, we'll get maybe, let's say, 2 or 3 features. We'll extract 2 or 3 meaningful features from that. And we'll do that while retaining most of the important information. So if you want to understand how we do that, you can see the video. So in SVD or Singular Value Decomposition, what we do is we do matrix factorization technique. It's a matrix factorization technique. We get a matrix and we factorize the matrix. We breaks down the matrix into meaningful parts, revealing its underlying structure by identifying, dormant features. So reducing noise and creating low dimensional approximation. So these are few general, normal, generic ways to do feature extraction in machine learning. Now, domain-specific feature extraction. So different domains will have different types of features. So if someone is expert in some domain, they will know how to extract those features. So in healthcare, we can extract BMI from weight, height. We can try to combine the lab metrics to come up with different meaningful, much more meaningful features. In biochemistry or bioinformatics, we can try to do amino acid sequence encoding, molecular fingerprints, gene expression vectors. So these are some domain specific features we can extract. So I just mentioned about two domains. So there are lots of other domains like financial domains, logistics and all. So different domains will have different domain specific features. And this feature extraction in machine learning, it depends on domain expertise. Now, what counts as a good feature also depends on the task, what we want to do with our data. So for a tabular data, it is very straightforward. We'll have some output defined, right? So if we have like height, weight, BP and all this given, and we want to predict the chances of some disease. So this is kind of specific output is given. So that is the task. For image data, we might like to do image classification, object detection like face recognition, emotion detection from the image, age estimation, medical scan image investigation. Like if we have CT scan or MRI scan images, we can try to investigate that. Identifying pedestrians, vehicle, traffic signs on road. So for autonomous vehicle, it can try to it can try to identify the pedestrians, vehicle, traffic signs, etc. For text data, if we have raw text data, we can try to do sentiment analysis. So let's say if customer is commenting or reviewing a product, we can try to understand whether it's a positive review or the negative one. Topic classification. So let's say if we are given some raw text, we can try to understand based on the words, phrases, context, what type of document it is. It is a sports document, politics document, or something else. Spam detection, search. These are few other tasks with text data. So of course, the feature we will extract will depend on the task we are performing. Now, drawback of traditional manually extracted features. So as we already discussed, we need domain experts to extract the features. And this is the main drawback in traditional manually extracted features. So we need domain experts and it is very time consuming. Also, it is hard to generalize. So the features are extracted based on the domain knowledge and we cannot generalize it to all the domains. Also, it doesn't handle raw image, audio and text well. So traditional ML feature extraction is basically manual domain driven one. So we cannot generalize it well and it's very difficult to do. We need domain expertise. It's time consuming and so that's where deep learning comes in. So deep learning reduces the burden of manual feature engineering. Instead of we defining the features, deep learning learns features automatically. So in traditional machine learning, what happens is we have the raw data. So let's say we have this image of a dog. This is a raw image. We are doing manually extracting the features. And then that we are passing through the model. So this model can be a normal neural network. It can be normal any other model. And then it will predict the output. In deep learning, what happens is we have the raw data, we directly feed the raw data to the network and features learned automatically when it will predict the output. So basically in deep learning, we assign the weights in all these layers, right? And we do gradient descent and backpropagation. And all these weights are learned automatically. So basically in different layers, maybe different types of features are extracted. So let's see this small example we already had here. So height, weight, BP, heart disease. So earlier we are calculating BMI manually. But what we'll do here, we'll just pass this data to this deep learning network and we'll try to maybe extract better features than BMI. We don't know what exact features it will extract, but it will try to assign the weights, and each layer, what deep learning does. So each layer, each neuron is basically a weighted combination of the previous layers, right? So it's a linear combination of the previous layers, and then we are applying activation functions. So we are getting non-linearity. So in that way, and then we are doing back propagation, right? And that's why how we are learning the gradients. And these gradients are used in gradient descent to update the weights, and we'll know the weights. Now let's see one simple different example. So we have few handwritten digits, and we'll do digit recognitions, handwritten digit recognitions. So 0 to 9 digits will recognize. So image is represented as a grid, right? So I am taking one simple grayscale image here. Pixel values will be from 0 to 255. So 0 minutes close to black, and 255 minutes it's close to white, right? So let's say these are the close to white, gray, grayish pixels, and these are the darker pixels. And this defines 7 here. So if we have a color image, so then for each pixel basically we'll have 3 values, one for red, one for green, one for blue, right? So each pixel value will be from 0 to 255. Now let's say here I have taken one simple 16 by 16 image, very small image. We'll just pass the image directly through this neural network. So 16 cross 16 image we can directly insert, right? So we have converted into 256 dimensional input. We have basically flattened the image, right? And we got a 256 dimensional vector. So that is our input vector. And it is going through multiple hidden layers. And in output layers, we have 10 output nodes. So each is basically outputting the probability of the prediction being that number, right? So this 0 will represent probability of output being 0. This will represent probability of output being 1, and so on. So we'll use softmax to calculate the probabilities here. So we cannot know directly like what features this network is learning, but this is our assumption. So the first layer might learn simple stroke patterns, pixel combinations representing lines and curves. Layer 2 might learn digit specific structures like loops, intersections, endpoints, etc. And at the output layer it will assign some probabilities to digits 0 to 9. So this is our assumptions, like what different layers might be learning. So the earlier layers learns small patterns, and as we move up, like the higher level layers learns complex structures from the image. So this works. So if we can directly fit the image, this deep learning network also will learn features, will extract features from this image. So this will work because this is a very simple image. So if we take any handwritten digits, right, the structures are very like simple, right? So this type of feature extraction will work with this type of dense neural network or deep learning network. But if we have a complex image, this feature extraction technique might not work, because this here we are flattening the image, right? We are flattening the image from 16 cross 16, we got it to 56 dimensional input vector. So it ignores the spatial structure. So let's say we have an image where we have some background, multiple few other background objects as well. So this facial structure will not be captured if we flatten the image, right? So it will ignore it is ignoring the spatial structure. It is sensitive to small shifts or rotations, right? Because we have flattened, right? There is no structure we are maintaining here. it will have more parameters than CNN. CNN is convolutional neural network, so that is the feature extraction technique we use in computer vision. I will discuss in detail in our next video about CNN. So CNN is used for complex images to extract the features. So doesn't scale well to complex images. So this, if we just feed the image directly to the deep learning network here, so it will not work for complex images. So this is also feature extraction by deep learning, but for complex computer vision tasks, we need better feature extraction techniques or maybe better types of deep learning layers. So that we'll discuss in our next video. Feature extraction for natural language processing. So, what does it mean in NLP or natural language processing? You are basically dealing with raw data, raw text data, right? So, in NLP, it focuses on extracting patterns from language. So, identifying meaningful patterns in text, such as words, phrases, syntax, or context, and converting them into numerical representations that models can understand. So we understand words, phrases, etc., context, etc., but computers just understand the numbers, right? So we have to convert these words or phrases and all to numbers. So unlike images, text has no pixels or spatial structure. So the challenge in NLP is to capture meaning, structure and relationships between words in a way that helps the model perform a specific task. So there are different feature extractions techniques for NLP. So traditional feature extraction techniques include one-hot encoding, bag of words, TF-IDFs. These are basically word count or frequency based approach. So if you are given some text, right? So certain words will occur in certain number of times, right? So based on the counts or frequency of the word, will come up with some representation. So that is one hot encoding, bag of words, or TF-IDF. One hot encoding, I think you already saw. It's basically some vector representation like this, right? So it will have one only in the position of the particular word. So let's say we are talking about a vocabulary of 4 words, right? It just has 4 words. So at the position of that particular word, we'll have one, rest will be 0. Similarly, bag of words, TF-IDF, all this we'll discuss in our NLP feature extraction video. Next comes deep learning based feature extraction techniques like word to wake, birds, etc. So, what is word to wake? So, word to wake converts any word into numbers, into vectors, right? So, let's say you take one word, book, right? It will convert it into some vector like this, right? So, these numbers are not random numbers. So, we'll start with random numbers, and as the deep learning models will learn, it will get trained, will come up with much better numbers here, and so that this book is represented well. So this might be thing we can think of as a like this minus 2.3, the first attribute it can be representing. If it is related to education, the second one maybe if it is for the people and all this, right? So we don't know what it is, what these features, what these values are, but we'll train it in such a way that book can be represented better in these vectors. And let's say we have two vectors, like one vector is, let's say, king, one vector, let's say, is the queen, right? So king and queen, these two vectors for king and queen will be similar, closely similar, not exact, but it will be closely similar. And we can also perform vector operations with this word to wake, like king minus man plus woman equals to queen. So this type of calculation, vector calculations, will be we will be able to do, because these numbers are trained in such a way so that we can do this type of vector calculations. So basically it captures semantic similarity. Semantic similarity basically is the meaning of the words. So what to make captures meaning of the words. Next comes birds or many other there are many others feature extraction techniques in deep learning. Bird is one of them. So it captures contextual meaning. So contextual meaning, what it is, let's say we have one word bank. So bank can be a financial bank where we store our money or we take loans and all, and also it can be a river bank, right? It can be a river bank. So how do you know what that means? Based on the context, right? So we have the raw text. So based on the context of the data, context of the text, so we can understand whether it is a like normal bank or it's a river bank. So the birds or this type of advanced feature extraction techniques in deep learning captures contextual meaning as well. Semantic similarities, of course, it will extract, and semantic similarity, and of course the contextual meaning. So all this we'll discuss later in our later videos. Next comes feature extraction for audio data. So what are the features in audio data? So if it is a speech, we can have pitch, formats, speaking rate, etc. If it is a music, it can have tempo, chroma features, rhythm patterns. I also don't know what these features means. If it is a medical audio, we can have heart sound intervals, lung crackle frequency, and all, right? So we'll feed the features directly into the deep learning models. Now, the feature extraction, this also will depend on the task, right? For the speech, basically our target is to understand the meaning of the speech. For music, we might have different types of tasks. For medical audio, right, we might like to understand we might like to measure something to predict the chances of some disease and all, right? So based on the task, for this audio data, we might need different features. Now, if traditional feature extraction for audio data includes, there are few handcrafted features like MFCC, speech, tempo. These are manually designed. So domain knowledge is required to choose these useful features. Features are fixed before training. Before training, we collect the features and then we do the training. In deep learning based feature extraction for audio data, it's the same as we saw for the computer vision and the NLP. So models learn features directly from raw audio or spectrograms. No manual feature design is needed. Features are learned automatically during training via backpropagation. So this for audio data also we'll see in our later videos how deep learning, how we come up with different types of layers and all to get better features for audio data. But our idea is almost always same. We might have different types of layers in deep learning, but we'll assign random weights, we'll do gradient descent with backpropagation, and then we'll learn the weights. That's how features are extracted in deep learning.